characteristics of a mixture and pure substance. What I have up here is some, what? Oh, yeah. What I have here, and I'll get it in the sunlight here, is I've actually, this used to look like this, but I took it and shook it up. I don't want to shake this one up because it looks so nice. But I made this before you guys were hatched, about 18 years ago when I first started teaching. Now, as I shake this and continue shaking it, everything's evenly dispersed throughout. But what am I doing? Shaking it. I'm actually putting effort, work into making it an even distribution. When I look at this bottle of Windex, do I have to shake it to make this blue nice and even, the ammonia nice and even? So these are two different types of solutions. This is a solution. This is a mixture. This is a heterogeneous mixture. This is a homogeneous mixture. In other words, homogeneous mixtures, we don't have to do anything to it. It's evenly dispersed throughout all the time, which is nice. However, as I shake this, it's evenly dispersed, but as soon as I stop, all the heavy things go to the bottom automatically. And then if I were to ask you, okay, if I come back an hour from now, will it still look like this? No, actually what's happening is the silt will settle and it'll form that nice little silt layer that you can see on here. Now, the water, I probably wouldn't drink it still. I mean, it's still got some particulates in there. But, I mean, but desperate times call for desperate measures. I definitely wouldn't drink that. Okay. So, when we talk about a mixture, sometimes you can talk about a homogeneous mixture and a heterogeneous mixture. Those represent two different solutions or two different types of things. Also, keep in mind that when we talk about a solution can also be a solid and a gas, not only a liquid. But whenever we think about solutions, generally that's what we're thinking about is the liquids. Like, for example, right now we're enjoying a wonderful solution right now. Air, very good. And air is made up mostly of what? Not oxygen, but nitrogen, good. And then that's about 78-ish%. And then oxygen comes in second, and then we've got some other things. So, but what I can't do is I can't say, okay, I've got this sample of air that we're all sharing here, and I'm going to hoard all the oxygen. I'm not going to let anybody over on that side have the oxygen. I'm going to keep it right in here nice and big. Can't do that. All right. When we do something like that, then we're looking at a mixture. Okay. Now, is it possible for me to separate this and just get the water away from this? Yeah. I can either do it one of two ways. I can filter it, which I think I have on here. I can filter it. It's somewhere down there. I'm trying to remember. Do you guys have the blanks here? Get those blanks. Mixture and pure substance. It wasn't? Okay. So, here, I'll come back to that in a second. So I can filtrate it, or I can filter it through filtration, or I can distill it. Now, I have an image of how you would distill something. In other words, if I heat, say I take that muddy water and I put it in there, the thing that has the lowest boiling point will evaporate out. And then I can condense it by running some cold water through there, and I'll get pure water out of that. So yeah, it is possible to get nice clean water out of that. Let's go back up. So when we talk about solutions, again, there's a homogeneous type and a heterogeneous type. So again, the homogeneous type, excuse me, is that beautiful Windex. That's a nice blue color. I don't know why they make it blue, but I guess it's more appealing than this because ammonia doesn't have a blue color. It's clear. And then a heterogeneous mixture is that guy. Okay. And looking at the images that I have here, like for example, I've got olive oil in the bottle on the left and then vinegar on the right. These are both homogeneous mixtures because the olive oil is spread out evenly throughout, so it's made correctly. There aren't chunks of olive in there. And the vinegar is made of acetic acid and water. But what if I put those two together, make salad dressing? How's that? Does that make a nice little solution? It tastes wonderful, yeah. And I made these a while back. Okay. So like when you look at it, get it So as you move it around, okay, so there's oil and water. Where do you think the water's at on these? On the bottom, very good. In other words, that's why I can put food coloring on there. So oil doesn't care for the food coloring or the water, and if I shake it up, kind of looks kind of delicious there, and actually it got lighter in color. But will this eventually go back to this? Yeah. Yeah. Okay, so we got to give it some time there. So, but that's one reason why if we have salad dressing, we mix these two together, we have to shake it up because they don't like each other. And that's okay. I know you've heard the term solute and solvent before. I know that because my son's taking biology right now, and they are talking about solute and solvent. If I had some table salt and I placed it in the water, what is the table salt acting as? Solute. The thing being dissolved. The solvent, water is the universal solvent. In other words, we like water quite a bit because most of the things that we eat are water soluble. We don't eat marbles and rocks. Hopefully you don't. If you do, then it's going to be a loud day tomorrow for you. Okay, so, don't do that because the body doesn't want that. Okay. All right. I think I already talked about those. So again, when I say the term mixture, mixture just means some type of solution. Did I give an example of a solid solution? I know I talked about air. If you have a brass water faucet at home, that's made up of copper, cobalt, some steel or iron in there, and that's evenly dispersed throughout. So solids can also be a homogeneous mixture that's dealing with hetero. Okay. So the 12s are part of your homework. States of matter. We've talked about states of matter real briefly. We're going to talk a little bit more about it today, but it's going to be super brief. Again, matter can exist in three common states: solid, liquid, and gas. A solid is a form of matter that has a definite shape. Okay, I don't have a solid up here. Maybe I do have a solid somewhere. Here we go. Like this little clip here is considered a solid, even though it's thin. It has a definite shape until I do something to it. Heat it up, change it, but as it's a solid, it stays that shape. However, if I look at a liquid, okay, the volume remains the same, but the shape changes as I move it around. So it's an indefinite shape. Same thing with a gas. I can take a gas and say, like, if you go to Kroger, Walmart, or whoever has the helium tanks, inside that tank is helium. But if you take the tank and like move it around, what do you feel inside? Have you ever done that? Go to Kroger tonight and grab the helium tank and start doing this. Just tell them, hey, my science teacher said I need to come here and do this. Actually, there's a liquid inside because it's helium. It's been compressed so much that gas has changed into a liquid. And if you take it and jostle it around, you'll feel that liquid shaking around as long as there's some helium in there. Same thing with propane tanks. If you pick up the propane tank while it's full and kind of move it around, you can feel the liquid. So we can compress gases so much that they actually change into a liquid. Solids, I can't compress a solid. I mean, yeah, I can squeeze it, but I can't compress it. Liquids, can we compress liquids? A little bit, but that's what we use for hydraulics. So we can compress it a little bit, but it's super strong in that it's very flexible. So when you look at a backhoe or a bulldozer or whatever that has the hydraulic lines on it, that's pretty strong. I mean, it can do some amazing things. So thank your liquids and your solids and your gases. They get underappreciated. All right. Now, here is something, a term that we kind of use interchangeably, gas and vapor. Okay. A gas is a substance like oxygen, nitrogen, things that are naturally a gas at room temperature. All right. A vapor is if I add heat to this and I cause a liquid to change into a gas, which is technically a vapor. If I had, say, dry ice and I allow it to sublimate, it'll turn into a gas, or a vapor, sorry. So gases are things that are at room temperature, that state. Vapor are things that change into the gaseous state. Okay. So if you should happen to see a question like that on the test, make sure that you answer it appropriately. Freezing point and boiling point, these are two temperatures at which we can use to help identify a substance. In other words, if I say the boiling point for water is what? 100. We can use that to help us identify that it's water. Now, we can also use freezing point as well. Now, the freezing point for water, and this is a good little question for you. If water freezes at 0 degrees, what temperature does it melt at? Okay. If it freezes at 0, what temperature does it melt at? Oh. Actually, it's the same. It just depends on whether we're adding energy or removing energy. Okay. So, and that's a great question that a lot of students are like, wait a minute. Remember that when we're freezing, we're taking energy away. When we're heating it, we're adding energy to it. We'll talk about phase diagrams a little bit later on, but that's always a question that causes students to go, what? Yeah, Hunter.
But can't water be like below the freezing point if it's like a big body of water?
We can supercool it, but it won't stay that way for a while. Now, and keep in mind, like if you were to say, pretend this was like Michigan. If I were to take the temperature of it down here, is it the same as up here? Obviously not. So that's why sometimes only certain parts of it will freeze because that's the one that's exposed to the rigid or the cold temperatures. So yeah, it's possible, thank God, that lakes don't freeze all the way to the bottom, or else we wouldn't be here. Okay. So I don't know. Did that answer your question? I don't think that answered your question. But the liquid is going to change. Now, it's kind of cool to see a liquid. No, I'm not going to say that. I have a demo for that later on. That's not today, though. When we have a super saturated solution, I can get a liquid to change into a solid like that. And it's about the same volume here. It's pretty cool. That's another day. All right. Again, when we undergo a phase change, going from a solid to a gas to a liquid or any one of those states, we keep in mind that that is a physical change. All right. The homework is the 12 through 16, and of course, study for the 52 elements.